Hi everyone, thanks very much for coming. My name's Sam Burns. I'm a software architect and application security specialist. As of very recently, I've been working with Go cardless. I obviously develop in Go and like to play around with CUDA, but I also work with Ruby and PHP. Can you believe they let a practitioner of dynamic typing on stage? I'm surprised I got past security. Okay, so I'd like to say a huge thank you to the GopherCon team for putting on this fantastic event, and what a beautiful city to do it in. I'm so glad I came. Okay, on with the show. I'm afraid I can't take any questions now, but feel free to reach out on X if there's anything you want to know. I'm not very chatty on social media, but you'll be able to get in touch with me to ask any questions. I'd like to thank Google and our other sponsor, CodePros, for providing the best Gopher in my deck. This is Cypher from The Matrix. There will be other Gophers, but I'm not an artist, so they're going to be of mixed quality. You'll be able to find a link to the slides on this blog. I'll upload them there tonight. And for those of you participating in the CTF competition, why not check out the blog now and see if you can find this guy. He might have something for you. And in the meantime, let's take a look at what we're going to go over today. So I'd like to start off with an intro to GPUs. I'm sure a lot of you have been hearing a lot about them recently, but we can take a look at the relevant bits of the architecture in a little more detail. I'd like to go over coding with CUDA and the basic anatomy of the language and toolset. I'd like to talk about what I'm calling high thread count programming, by which I mean the massive parallelization available when we integrate CUDA and GPU programming into our Go applications. I'm going to go in a little bit more detail over Go, CGO, and CUDA and how that actual integration works. There will be some Go code on screen at some point, I promise. We'll take a look at a practical example, linear algebra, and talk a little bit more about performance optimizations and some tips on how to squeeze the most juice out of whatever GPU you can afford. But before we go any further, could I just ask, out of interest, how many people in the audience have used CUDA before? How many of you coded in CUDA? Oh, okay, cool. And just to help me calibrate that, how many of you will put your hands up if I ask everyone in the room to raise their hand? Okay, about 3/4, so more than I thought. Okay, great, thank you. So let's take a look at an intro to GPUs. So once upon a time, we had to make do with single or dual core CPUs when we were coding. CPU cores are great, they're fantastic things. They have low latency, excellent caching, branch prediction features. They have dedicated acceleration for common tasks such as AES, for example. If you've seen any of my other talks, you'll understand why I care about that one in particular, but this can speed up writing to encrypted disks, HTTPS communication, stuff like that. One disadvantage is that there are often about a dozen on a laptop, seldom more than 100 on a processor, on a server, sorry. GPU cores, on the other hand, have a high latency. They're much slower for a lot of tasks. They tend to lack powerful optimizations of CPU cores. On the plus side, there can be thousands or even millions of them. This means GPUs are well suited to tasks where calculations are simple, but where massive parallelism is an advantage. The initial example, of course, was computer graphics. So to take a look at the timeline in a bit more detail, graphics cards were around in the 90s. From the look of the audience, some of you weren't, but I was. In the early noughties, we had programmable shaders. This means where a graphics card essentially hardwired just to do shading problems. Programmable shading means trying to turn whatever problem it is you're trying to solve into a shading problem and then solving it on a shader. And this is kind of why NVIDIA created CUDA in 2006. So this, for the first time, allowed arbitrary mathematics, linear algebra, etc., to run on GPU hardware. In 2012, something very important happened. A team at the University of Toronto tried using them for something else as well. Krzyzewski, Sudskiva, and their PhD advisor Hinton built an image classifier, a machine learning model that ran on 2 graphics cards, 2 GPUs using CUDA. Artificial neural networks require the same massive parallelism and of simple calculations as graphics does. So now, of course, that idea has been taken a little further with some quite prominent results. Now, to take a closer look at CUDA and what it's used for and how it works. Compute Unified Device Architecture, or CUDA, is a C-like programming language for GPUs. There is a language beneath that you can think of as metaphorically like machine code called shader assembly, or SAS. Above that, we have PTX, which allows orchestration of parallel threads, parallel thread execution. And built on top of PDX, we have CUDA. CUDA reads a lot like C code. Like C, you should be able to run it on multiple devices. So some very clever people at NVIDIA have gone to great lengths to ensure that it works across different GPUs, etc. This allows developers to transfer data from the host, by which I mean the CPU, to the device, meaning the GPU. And CUDA can orchestrate threads, use GPU memory internals, which we'll talk about a little bit more detail in a moment, and return results back to the host again. CUDA's a programming model. It uses kernels, which are functions that run on thousands of threads across GPU cores. It has a runtime API to manage GPU memory, launch kernels, and sync with the CPU. And CUDA has a compiler toolchain, NVCC, translates CUDA into the necessary GPU machine code. Now, to look at what we might use that for, graphics programming is the obvious and original example. Image processing, video transcoding, video editing applications, things like that. Perhaps one of the reasons why we want to talk about this is machine learning and artificial intelligence tasks. AI model inference and training. Neural nets need massive parallelization, but the underlying mathematics is often somewhat simple. I wouldn't say very simple, but it's something that can be run on a GPU core. And physics simulations. This can include aerodynamics, for example, quantum mechanics, quantum computing. If we're to have any luck in simulating quantum computers on classical hardware, a lot of the time a GPU can be the best way to do that. And there are other applications as well. Obviously, you've got password cracking, cryptocurrency mining, graph analytics, the list goes on. Now, to take a close look at CUDA and how you go about programming with lots of threads. This is my first animated Gopher. This one was a dry run. The next one will be better, I promise. So to take a closer look at CUDA, what it's used for, how it works, we're going to need to bear a couple of things in mind when we're working with CUDA. The first is a thread model, and the second is kinds of memory available. So imagine, if you can, New York, a grid that's made of blocks. Let's take a top-level look at threads, blocks, and grids in CUDA. A kernel is a C-like function compiled for the GPU. You launch it with a configuration that says how much parallelism you want. Threads are the smallest unit of GPU work. It's essentially a loop running in parallel. I often find it helpful to think of them as comparable to Go routines, kind of. A GPU may be able to run many thousands of these at the same time. When we group threads together, we group them into blocks. Threads inside the same block can cooperate with fast on-chip shared memory and can synchronize with a function called sync threads. Threads and different blocks can't directly sync. The grid is all of the blocks launched for a given kernel. So this is a little simplified in places. There are some other things as well. I didn't mention warps on the slides because we don't need to interact with them very much when we're writing our first CUDA code, but a warp is a group of 32 threads, which is the performance of your code will depend on them, but it's basically just a thing for the hardware scheduler. Now, the thread model and GPUs, thanks to NVIDIA for the diagram. A CUDA thread runs on a CUDA core on your GPU. A block of threads runs on what we would call a streaming multiprocessor. And a grid is all of the blocks being used for a given kernel. So it's possible to fill up the entire GPU with blocks of threads for one kernel. It doesn't have to be done like that, but you can. There are a lot of different kinds of memory available here. Some of these you definitely do need to understand. Some of them you can get really quite a long way without looking at, but we'll go over a couple of the more important parts. Registers are per thread. They're the fastest kind of memory available. The compiler keeps frequently used scalars here. If you try to use too many, however, then it spills over into slower memory. The local memory is on a per thread basis in device DRAM. Despite the name, that's off chip. It's on the device DRAM, but it's not on the chip, if you see what I mean by that. So it's used for spills or large per thread arrays. It's best to avoid using it if possible because it's a little slow. Shared memory is per block on chip. It's a user-managed scratchpad, tens of kilobytes per block, possibly hundreds, it depends on your hardware. They're great for tiling, staging, reductions, and avoiding repeated global loads. They require explicit synchronization with the sync threads function, which we'll look at later. Global memory and device DRAM is grid visible. It's large, you can measure it in gigabytes, but it's much higher latency for reading and writing. All threads can read and write to this, to the global memory. And there are a couple of other kinds as well. Constant memory, for example, good for parameter tables. Reference data is very broadcast friendly. Access is quite quick. There are L1 and L2 caches that work too. These are device managed, but important during performance optimization. So if we have a look at another diagram from NVIDIA, there are some specs on the screen. This is specific to an A100 GPU, but the principles are kind of the same no matter what hardware you're using. So this is a diagram of somewhat we've just discussed. Here we have streaming multiprocessors, each depicted as having their own registers. Registers are private to a thread. They have an L1 cache, 192 kilobytes on A100, shared between threads. The read-only memory or constant memory is good for providing reference data to threads. Global memory is slower to access. And an A100 GPU, there are 40 gigabytes. This size is important to anyone who's ever tried to load a model into VRAM and do inference, for example. Really, the important takeaway here is that accessing global memory is slower. Transferring data to and from the device and between the device and the host, however, is obviously being done via a PCIe bus, so it's much slower than that. So armed with some information about CUDA's threads, the thread model, and the memory management situation, let's move on to the next section and look at Go, CGO, and CUDA. Okay, this one is probably my best Gopher, obviously not including Cypher, and other ones I made. So to jump into a couple of code examples, we can look at some Go code that uses CGO to call out to C. We can then have a look through the C function it's actually calling, which will invoke a CUDA kernel. This is a really simple coding example. All it does is increment numbers in an array. We're thinking about how to integrate Go with CUDA, so really the scaffolding is the interesting bit here. So to take a look at the top part of our Go code, what we can see is a CGO annotation for making breakout C available. As part of that, there are some flags here. It's worth noting that there is one of those is a path to the CUDA installation. This is obviously system and architecture specific. There's a reference to the CPU chipset in there. So you're going to want to do your development on an environment that's at least somewhat production-like here. You need some parity between production and development environments. The part where it says -L add one, that's a reference to a function that we're going to write in CUDA. So this is a reference to a compiled CUDA code locally that we'll take a look at the moment. And we can see we've added the function signature of the relevant C code. And we're importing the C library to enable us to call out to that from Go. Looking at the bottom part of the Go code, it has c.add1, so this is this reflects the function signature that we saw a moment ago. This is what's wiring together our C code and our Go code. The C invokes CUDA kernels, and we'll take a look at that in a moment. I don't want to get too focused on what the business logic does. It's just adding one to some numbers. But the unsafe pointer library, so we've imported the unsafe library. The unsafe pointer, what we're doing with that is, it's important to remember that we've got a language which does manual memory management and a language which has the garbage collector combined. In fact, Go actually has a choice of 2 garbage collectors, and if you're still in this room in a couple of hours for Michael's talk, you'll be able to find out more about the green tea garbage collector. But basically, regarding the comment about not letting C keep the pointer, it's just because we don't want Go's garbage collector to free up that memory. So we're not going to refer to it in C after it's returned. It'll live for the length of the C Go call, but we're not going to refer to it after that. So this rule ensures that we don't dereference a stale Go address from C after the call, because the Go object may not be there anymore, or it may not be at that address. We don't want to get too bogged down in the details here. If you're just trying to get this working for the first time and having problems along those lines, a beginner-friendly tip might be to just throw runtime.keepalive at the problem and see if that fixes it. So this is a way of communicating to the garbage collector that an object in memory is sacrosanct. So to take a look at the CUDA code that we're integrating with here, excuse me. This is the top part of the CUDA code. We've called the file add1.cu. At the top is the CUDA kernel. I find it helpful to think of this as being a little bit like a function that you might call from lots of Go routines. There will be loads of these running at the same time. It's not super interesting in what it does, but what's interesting about it is really the parallelism and how you invoke it. So it's just incrementing an array, but it's giving each thread an index number based on its block number and its position within the block. So this ensures that each element gets incremented by a thread only once. Global here on line 4 means callable from the CPU but running on the GPU. Extern C disables C++ is name mangling just so that CGO can link to add1 by its exact symbol name. We need that name to be unmolested by the compilation process. It's just some boilerplate to make sure that we can actually integrate the CUDA with the Go nicely. The types we use in our parameters in the signature were chosen for easy compatibility with other languages here. We had to use unsafe pointers earlier because the Go float32 type is the same punished shape as the relevant type in C, but they remain distinct types, so we're using the unsafe package. But we still want to try and stick to parametric types, which are going to be easy to work with here. D is our device pointer, and then we're allocating device memory, meaning GPU memory, with a memory allocation or malloc. After allocating memory for the device, we can then copy data from the host to the device. There's a PCIe bus involved here. In my case, this makes this a very slow step. That data transfer is slow. Optimization sometimes means thinking about what you copy to the device and what gets calculated on the device. The memory transfers will be where a lot of the time goes, particularly with such a trivial example. We then set up a thread count. Although it's overkill for what we're doing, I've gone with 256. 256 is a common choice. It's divisible by 32, so it's warp friendly. The device's scheduler will like that. We use the number of blocks and threads per block to launch a kernel. So if you remember in our kernel here, it's using that to work out for a given thread which element in our array it's supposed to be incrementing. So each thread has a job to do. And then we copy the results back from the device to the host. Before doing that, I have synchronized the threads here. This was kind of a readability choice. There is a subsequent line that would have forced that to happen anyway. But I found it better for readability here just to make the point that they do need to be synchronized somehow. If it helps you as a Go developer, you can think of that as kind of comparable to Go's sync.waitGroup. And such code in practice would often call CUDA.getLastError, but we can omit that for simplicity here. So when it comes to compilation and execution, we're compiling our code with NVCC to turn add1.cu, the CUDA file, into libadd1.so, which is available to Go. Remember that we used the extern keyword to ask the compiler not to mess around with the function name. So this should be perfect for accessing directly from our Go code. We need to make sure that the library is available to the Go compiler, LD library path, which I guess stands for library directory, is giving a hint as to where the CUDA library is. Go runs, and it's not spectacular in its functionality, but since we've integrated Go with CUDA, remember how much further you could scale this without any noticeable slowdown. Even on my domestic hardware, which was a GPU worth about $250, we could scale this up 1,000 times and still do all of the arithmetic in parallel. And now to look at a slightly more practical example, as we've still got time, we're going to extend our scaffolding to implement matrix multiplications, which is a firm favorite for all you linear algebra fans out there. So let's start with the Go code. Once again, we're starting with the CGO comment. Here we have a reference to matmul, which is our matrix multiplication library in CUDA. We're going to generate some random matrices, so we'll import the necessary packets to do that. And we're exposing the function signature of this C function that we're going to create, which is itself then going to shell out to the CUDA functions, or to the CUDA kernel. Remember that there are references to local paths here. There's even a reference to the CPU architecture in the path, so this would need to be done on production-like hardware. So let's multiply 2 by 3 matrices by 3 by 2 matrices. We'll create 250 of them at random. Even on cheap consumer hardware, we could probably do 40 such blocks running in parallel, no problem, but we'll stick to a single 16 by 16 grid for now. Nothing too adventurous here, we're just prepping our matrices and preparing the output array. And if we have a look at the bottom of the Go code, we see c.matmul, so that ties in with what we put in the function signature that we imported in our cgo annotation. And all we have to do then is just print the output. So to take a look at what the CUDA is going to look like for a slightly less trivial example than last time. Matmul.cu, our CUDA file that does matrix multiplications. The kernel goes at the top. Global means it's called from the CPU, runs on the GPU. Our kernel does a very simple linear algebra calculation here. And scrolling down to the meat of the C code, we can see that we're creating a single block of 16 by 16 threads with the capacity to handle more blocks if needed. For demonstration purposes only, we're only going to use one block here. The kernel is invoked, and the result is copied back from the device memory to host memory. This is actually the slowest part of the operation, along with getting the data from the CPU to the GPU, the actual problem instances, returning them again. These are still the slowest parts of our program. And all that has to do is invoke this CUDA kernel once for every matrix multiplication we want to do. So compilation and execution, running the code, same as before. We can compile the code with reference to our mapmul.cu library that we've written. We try running the Go, and we receive 256 matrix multiplications, all of which happened at the exact same time in parallel in CUDA code integrated with our Go software. Now, we've got a little time left, so we're going to take a look at performance optimization. This isn't a talk about profiling Go code. I heard that Corey's tutorial here at GopherCon went very well. There's a lot to be said about how to profile Go code, but we're not going to look at that now. We're just going to look at how to analyze the performance and do benchmarking and optimization on the CUDA side of things. So we'll cover NVIDIA Nsight suite. There are two parts of that that are particularly relevant here: Nsight systems and Nsight compute. These are two parts of NVIDIA's Nsight suite. I'd suggest you learn these two first. They're part of a bigger tool set, but these are the ones that are going to be most useful to you. Nsight systems is for profiling the whole timeline. So that starts from CPU usage, host to device to host, memory transfer, looks at kernel launches, etc. Once you've identified a particular kernel of interest, compute is better for zeroing in on a kernel. So it can tell you if a kernel's CPU bound or if it's having memory issues, or give you other information that can help you understand why a given kernel is hot. So Nsight Systems is a system-wide performance profiler that gives end-to-end timeline across CPUs and NVIDIA GPUs, showing CUDA API calls, the memory copies, kernel execution. You can spot bottlenecks and opportunities for enhancement. Collections done by running nsys-CLI actually on the target machine. This might be a server or a container, for example. You then take the resulting trace and open it later on the desktop GUI for interactive analysis. A typical workflow might be to record a short run using nsys profile, inspect whether transfers overlap with kernels, identify idle gaps or excessively fine-grained launches, and then once you've identified a hot kernel, switch to Nsight Compute for per-kernel deep dive. Nsight Systems is a fantastic tool for visualizing how data is moved around your system and how parallelization is working and where optimization is most likely to be successful. Nsight Compute, interactive kernel-level profiler. So this is with regards to one kernel. It collects metrics via hardware counters and software instrumentation, offers automated suggestions and issue identification ordered by severity. You can see an example on the right of what it's highlighted and what it's telling you to look at in what order. It's quite an opinionated tool that guides you in the direction of analyzing your code's performance in a certain way. And it provides what it calls a roofline view, which can classify kernels by memory or compute bound and guide the next optimization step. And this is a very useful tool and part of a process. I'd suggest, as I say, using systems first and then compute. Compute shows more detailed analysis of one kernel. Nsight Systems can help you identify issues. Compute helps you zero in on what you need to do to fix it. Okay. So now that you know a little more about how to profile your CUDA code, as well as how to integrate it into your Go application, go and have fun with it. And thank you very much, everybody, for your time and attention. I hope you have a wonderful time at the rest of the conference.